The next one is shock polar. So this is the definition is it is a graphical representation of oblique shock wave properties. In the theta, beta, m also oblique shock wave properties where we related theta, beta and Mach number, right? So here we are going to relate m1, theta and m2. Okay, this is the another form of oblique shock wave properties. So in this graph we are relating m1, theta and m2. Previously we related m1, theta and beta. Okay, this is the difference, and this is the whole graph. So here they are taking, so mx star, my star. That is, if you take m, it will go up to infinity, but instead if you take m star, it will go up to 2.45, and this is for different Mach number 2, 4 up to infinity. So for example, I am taking Mach number 2 and initially theta of 10 degree. So now see how to calculate m2 from this graph. So this is the Mach number 2 graph, right? So this line alone I have taken here, okay? Assume here other lines are there. I have taken only the Mach number 2 line. And this is the sonic line. And okay, so Mach number 2 I have taken. And now the theta is 10 degree. Then how to draw the 10 degree means from this axis, you have to draw the line for 10 degree. Okay, so you'll get two intersection point. Is that clear? This is for Mach number 2 curve. Now my theta is 10 degree. Simply you have to draw the line for 10 degree. You'll get two intersection point. And this is the sonic line. And how to find m2 means the magnitude of this line is the m2. Okay, so m1 is 2, theta is 10, and this line magnitude gives the m2 value. And here I am getting 2m2. So this is subsonic, this is supersonic. You know, subsonic means strong solution. That is, this is the sonic line. Below that, we will get the strong solution. It is omitted. So only this intersection point you have to take it. Okay. For example, if theta is 20 degree, then from here you have to draw the line for 20 degree. Now we are getting one intersection point, and the magnitude of this line is the m2 now. Now I am increasing this theta to 30 degree. For example, it crosses here, and we are getting only one intersection point. Now this will be our m2 for 30 degree. And if I further increase the angle to, for example, 35 degree, there is no intersection. That means the shock is detached. Okay. So within that, the shock is attached. And after that, the shock is detached. Okay. So depends upon the Mach number, you have to choose the curve. Then depends upon the theta, you have to draw the line. Okay. You will get two intersection points. And these points are for strong solution, neglect it. Only this intersection point you have to take it. This is a weak solution, and this line magnitude gives the m2 value. That's it. So once you know the Mach number 1, that is 2, and theta, by measuring this, you can find the m2. Okay. So here also you can find the theta max for all the curves. So below that, strong. After that, weak. Like that, it will go. So it is almost similar to the theta beta m, but here we are relating m1, theta and m2. Consider a ramp in the supersonic flow. There will be a single straight oblique shock wave. Straight line. Okay. So single straight oblique shock wave in the normal case, but instead of this straight wall, if I am taking the curved wall, so you know curve means it will have n number of turning angle, right? See here the theta is fixed, only one theta. But if it is curve, the curve will have n number of turning thetas. So here, so this type of oblique shock wave it will be produced. So n number of weak shock waves from this curve, and everything will join after some distance. then it will be merged as a single oblique shock wave. Is that clear? Instead of straight wall, if I have taken the curved wall, it will have n number of turning thetas. So it produces weak waves and everything merges at some point. After that, it will be a single oblique shock wave. And weak wave, you know what it is? This is a Mach wave. So Mach wave means, so there is a small change in flow direction and property. So the P0, T0 is constant. The flow is isentropic across these waves. And here there is a sudden change in flow direction and property. So here P0 is not constant. So this type of phenomena they observe. So we are calling this as isentropic compression. So here also compression will happen, but it occurred across the infinite number of Mach waves. So it is very smooth and it is isentropic. There is no loss. So all these supersonic vehicles, hypersonic vehicles, in the inlet, if you see, it won't be straight. It will be like a curve. For example, I have taken this X43A, so hypersonic vehicle. So this is this scramjet engine, and this is the inlet. See, it is curved. It is not straight. Okay, if it is straight, it will produce strong oblique shock wave, then higher compression rate, then higher drag. Instead, they are taking this isentropic compression inlet. Okay, so it will produce n number of weak oblique shock wave, and that will get reflected within this scramjet engine. So because of this weak oblique shock wave, it will produce less drag compared to this single oblique shock wave. So it is a hypersonic vehicle which is successfully flew for the Mach number 9.64 and the duration of around 11 seconds, I think. Initially, it is taken by the B-52 carrier up to certain height around 40,000 feet. After that, to achieve the supersonic flow, we use a Pegasus booster. It went up to 95,000 feet. So once it achieved this Mach number, then they release this hypersonic vehicle X43A. Then it flew for 11 seconds with a Mach number 9.64. At last, then it fell into the ocean. Okay, this is the first successful hypersonic vehicle test. So you might have known. So here and all, they will use the isentropic compression. Okay, so this type of inlet they will have it. Okay, next one is multiple shock system. Actually, we are going to solve the problem using this. So here I explained only the results directly. So the multiple shock system, we are comparing the stagnation pressure loss, across the single normal shock and across the multiple shock. That is oblique shock followed by the normal shock. So if you take the normal shock, I am taking same Mach number in both cases. Across the normal shock, I found the stagnation pressure ratio is 0.3283. That means the P0 is around 30% the P0, so around 70% loss. Okay, so normal shock converts Mach number 3 to 0.4752, so very high compression. So because of that, the P02 is reduced to 30% of the P01, so loss is 70%. Now for the same Mach number, I am taking multiple shock system. So first oblique shock wave, then normal shock wave. Okay, so here this Mach number 3 is finally converted into Mach number 0.5956. So oblique shock converts high supersonic to low supersonic from 3 to 1.9 around 2. The normal shock converts supersonic to subsonic. And across the oblique shock wave, first you have to find P02 by P01. Then across the normal shock wave, you have to find P03 by P02. Okay. From this relation, I can find the relation between P03 and P01. Station 3 and 1. That is how much there is a loss in that stagnation pressure after the multiple shock system. So if you simply multiply P03 by P02 into P02 by P01, you will get P03 by P01 value. Here they found the loss to P03 is around 60% of the P01. Okay, here only 30%, but here it is 60%. So loss is 40%. So our aim is to minimize the loss. That's why instead of the normal shock, we are trying to produce this multiple shock system. Okay, so here loss is 70%, here loss is 40%. So in the practical application, instead of the single normal shock system, we are trying to produce this multiple shock system. So previously, it will be like a simple duct which produces the normal shock. Then the P0 loss will be very high. And nowadays, we are using this inlet cone. Okay, the idea of this inlet cone is to produce the oblique shock followed by the normal shock so that we can reduce the stagnation pressure loss. And this also we discussed shock interaction. If both sides having the same angle, it will be like a mirror-like structure. So this shock is called incident shock, and this is called refracted shock. Okay, so both sides same angle, so mirror-like structure it reflected. And here it is different theta. For example, 20, 30 we discussed. So this is strong shock. This is weak shock. So depends upon that we are getting the different deflection, that is refraction angle. So finally the flow is deflected towards this the low angle ramp. So here Mach number 3 to, for example, 2.5 Fahrenheit 2, it is reduced. For example, every angle. This is a streamline pattern. It is straight. Then another one deflection. Again another one deflection. So finally Mach number 2 we are achieving. Here this is a strong shock. Maybe 3 is converted into 2. Then 2 is converted to 1.5 here. So we have two separate Mach number, and in between that we are having one sliding line. This is called slip line. And condition for the slip line is constant pressure across the slip line. This we discussed. And this is the last case, special case. So normal reflection we know. For example, if we have a very high supersonic Mach number, for example 3, it will produce a strong oblique shock wave. And if there is a wall, the strong oblique shock wave will hit the wall and it will be reflected back. Okay, so this is the incident shock. This is the reflected shock. Okay, and this is a streamline pattern. It is straight, then deflected parallel to the wall, and always the flow has to be deflected parallel to the wall. So here it is deflected. Again, this flow has to be deflected parallel to this wall. So now this is our final streamline pattern. Okay, here straight, another one deflection, and this oblique shock wave again turns this flow to parallel to this wall. So this is the flow pattern, you will get it. So this is called regular reflection, and this is the special case, Mach reflection. Okay, this is regular. So next one is the Mach reflection. So Mach reflection, we are experiencing this type of shock wave in many conditions. So this is one example. This is another example. This is another example. We will see one by one. So in the first example, assume the Mach number is very low. That is minimum Mach number to produce the oblique shock wave. Okay, it is the minimum Mach number to produce the oblique shock wave. So assume the the oblique shock wave is extended up to certain distance. Okay, if the Mach number is very high, it can produce strong oblique shock wave, which can hit the wall and can be reflected back as a single straight oblique shock wave. But this is very weak, low Mach number, so produces weak oblique shock wave. Assume it couldn't extend up to the wall; it stopped up to here. After that, it will become like a Mach wave or something else. Like this, up to that only we are getting the oblique shock wave. So in that case, nature adopts the flow. So I already explained. This is the free stream flow direction, and behind this wave, again the flow has to be parallel to this wall. Okay, so the flow should be parallel to this wall. According to that, now nature adopts the conditions. So here we are having the oblique shock wave, but it is the strength is very less, so it couldn't project up to this wall. So in that case, nature create another one normal shock wave. So the flow adapts and creates another normal shock wave from the wall to this point. Okay, then from this intersection point, another one weak oblique shock wave propagate, and this type of Y-like structure we are getting. So oblique, normal, from the intersection point, another one oblique. So now what happens? So this is the original flow direction. So it is turned parallel to this wall. Okay, again, there is another one, what is it? Refracted wave that again changes the flow direction parallel to this wall. But here it is just a normal shock wave, so there is no change in flow direction. It's just straight. Okay, and this is normal shock wave, which will convert supersonic flow to subsonic flow, and this is oblique shock wave, which will convert high supersonic to some low supersonic. So here we have supersonic, here we have subsonic. So there is a difference in Mach number. So there is a sliding line that is called slip line. Is that clear? So minimum Mach number. So it couldn't produce strong oblique shock wave. So this weak oblique shock wave extended up to certain distance. It couldn't hit the wall, but flow has to be parallel to this wall, became that oblique shock wave. So the flow adapts and creates normal shock wave from the wall. Okay, from its meeting point, there is another one oblique shock wave. So now this flow is turned parallel, and here it is already parallel. So that finally you are getting the parallel flow to this wall. So here subsonic, here supersonic. So there is a slip line in between that. This is the special case of Mach reflection. Is that clear? So this they okay. This they observed in the experiments. So this is one example, and this is another example. For example, we know in the supersonic flow, if you place the bluff body, this will create the bow shock, right? Okay, if there is no wall, what will happen? This bow shock will extend up to certain distance, then it will be vanishing. Okay, that is normal shock wave, oblique shock wave, then it will become the Mach wave, then it will vanish. This is how the bow shock will happen. But here, special case, here we have the wall here. Okay, so because of the wall, this flow has to be straight. So here what happens? This is normal, this is oblique. Already it becomes weak and it going to convert as a Mach wave. But because of this wall, if there is a Mach wave, then it cannot process further. So it creates the normal shock wave. Okay, so it is become weak. From the weak oblique shock wave point, flow adapts and creates a normal shock wave, and from the intersection we are getting another one oblique shock wave. Now the flow changes like this. It is straight to this wall. Here also normal shock wave, it is straight to the wall, and here it is subsonic, here it is supersonic. So there is a slip line. So here different parameters, here different parameters, Mach numbers. I think pressure this is. Okay. Subsonic, high pressure, so red color. Supersonic, low pressure, so it is in yellow and orange combination. Is that clear? If there is no wall, then there won't be any Mach wave. It will be simply like a Mach wave and it will be vanished because of the wall. So we are getting this Mach reflection. This is another example, and here third example. So this is normal reflection. If the Mach number is very high, there will be a normal interaction. Then this is the refracted wave. But if the Mach number is less, then it cannot produce strong oblique shock wave up to this point. So this creates the Mach wave in between, normal shock wave in between these two. Okay, so here subsonic, here supersonic, here also supersonic. If both have same theta, it will be straight, but here it is different. That's why the flow is little bit deflected towards the low angle edge model. And there is a slip line, supersonic, subsonic, supersonic, subsonic. Let's go to the numerical problems. So first is very simple. So they are talking about the Mach wave. So they mention Mach number of the supersonic aircraft and the horizontal distance it traveled. What we have to find is the altitude of the aircraft. So once you know the Mach number, using the Mach wave angle, that is the formula, you can find the Mach wave angle. It is 42 degree. I think this was asked in the exam. And once you know this angle and this distance, using right angle triangle formula, you can find the height, just 500. This type of problem already we solved in the first unit itself. Here we are going for the oblique shock wave. So in this problem, the upstream properties are given. So Mach number is given, pressure and temperature is given, and they mentioned the beta value. I said usually they will give Mach number and theta, but in that case instead of theta they mentioned the beta. Beta means wave angle. Wave angle should be measured between free stream flow and this wave. Okay, this is beta. It is given. We have to find all the downstream properties. Now you can tell the procedure, how to proceed. Hello? We know M1.
So we can find Mn1.
Okay.
And using isentropic table. Then the isentropic table we can find Mn2, and then we can
First
find
tell the
M2.
formula. First tell the formula for Mn1.
Mn1 equals to M1 sine beta.
So M1 sine beta. Okay, you know M1 and beta, you can find the Mn1. Then? From
the table, sir, isentropic, we can find Mn2.
Isentropic?
No, sir, normal shock.
We have to use normal shock. There is no separate table for oblique shock. We have to use normal shock table. Then you have to find
Mn2, sir.
Mn2.
And then M2, sir.
You can find P2 by P1, T2 by T1, P02 by P01. All the ratio from the table, so you can get it right. So,
yes, sir.
Okay. So we know the P1, T1. So we can find P2, T2. Tell me how to find the M2.
So we have M1 and theta, beta. We can find theta from the graph, from M beta theta graph or not.
Okay. Can you tell the theta value?
1 second.
You use the graph and tell me at least approximate theta value. So M1 is 4, beta is 30 degree. For that, what is the theta value?
40, sir.
Around 40. Okay.
Yes, sir.
Okay, let me check. Okay. Okay, good. Okay, once you know the Mn2, beta, theta, you can find M2. This also we found. Then remaining P02, P02, S2 minus S1, how to find it? So once you know this ratio, you can find this S2 minus S1, right? What is the formula? I think minus R ln P02 by P01, right?
Yes, sir.
Yeah, directly you can substitute this value here. R value you know, you can find S2 minus S1. Okay, this also solved. Now remaining is this T02 and P02. Of the oblique shock wave, you can apply the isentropic. Behind the oblique shock wave, you can apply the isentropic. Only across the oblique shock wave, you cannot apply it because it is non-isentropic. Okay. So here you can find, once you know M1, P1, T1, you can find P01, T01 using isentropic relation. Similarly, once you know M2, P2, T2, you can find P02, T02, etc. and all. And across the oblique shock wave, P01, P02 will vary, but T01, T02 will not vary. Okay. So T01 is equal to T02. Either you can find T01 or T02, it's up to you. And from the isentropic table, as you know M2 and P2, you can find P02. Otherwise, from this ratio, if you want to use M1, P1, first you have to find P01 using isentropic. Then substitute here, you will get P02. Okay. So this procedure you are clear. So here I can apply isentropic. I know M1. I can find P1 by P01, T1 by T01, T1 is known, so I can find these two parameters. Similarly, just now we found the M2 using isentropic table. I can find P2 by P02, T2 by T02, T2, P2 also just now we found it, so you can find P02 and T02. Either way you can use it. So T01 will be equal to T02, and to find the P02, this way you can proceed. Otherwise, once you know the P01, from the P02 by P01 relation also you can find it to find it. So first they are finding M11 from M1 and beta, it is 2. And once you know this M11, using the normal shock table, they are finding other parameters Mn2, P2, T2, P02. So we know P1, T1, they are finding T2 or P2. And from this ratio, they are finding S2 minus S1. Everything is in SI unit, no need to worry about it. And once we know the M and 2, we can find the M2, but theta is the unknown. What you said 40, it is just 17. You can use this formula or graph. See in that graph, here theta, here Mach number, here beta. Okay, you have to take beta and Mach number. From that you have to find the theta. Okay, right? Beta is 30. This line, and Mach number is 4. So this is the Mach number 4 line. So here I am getting the intersection point. And if you come down, what is the value here? 16, 17, 17.5 something is complete. 17, 19, 90, 20. Okay. This around 17.5 I am getting from this graph. Theta is 17.5 degree there, we got it, but here it is accurately 17.7. So because of this theta value, everything will vary little. So to find the M2, now we found the theta. So M2 also found it, and we know T01 is equal to T02. So here from M1 they are finding using isentropic table T01 by T1. From there you can find the T01 because T1 is known. Then again for P02, using M2 they are finding P02 by P2. P2 is found, they are finding P02. But instead of this step, using this step itself, we can find P02 by P2, P02 by T2. T2 also know, directly you can find P02. And next problem. So across the oblique shock wave, they mentioned the Mach number and pressure. Here also they mentioned the beta wave angle, and we have to find P02. So the theta is unknown. So how to find P02? So we can find first Mn1.
Yes, sir.
Then
sir, we can find from normal shock table the P02 by P01 ratio.
okay.
And isentropic table at M1 we can find P1 by P01 ratio.
Okay.
Or P01 by P1.
Okay.
We can find P01 from here, and then we can put it in that ratio. We can find P02.
I found Mn1, it is 1.8. Then using the normal shock table, I have taken the ratio P02 by P01. The same way I followed, I think. Then again, using M1, I found P01. Then substitute here, you will get P02. Okay, good. In this problem, so here they are given M1, T1, P1 value, and theta it is mentioned 22.2 degree. You have to find M2, P2, T2.
We can find then P2 by P1, T2 by T1 ratio.
M1 we can find. What is M1 formula?
M1 sine beta. And from the graph table, M1 theta, we can find beta.
Can you tell the beta value?
It will be around 43 to 45, sir.
Okay, 43 to 45. Okay. So once you know the beta, you can find the Mn1. Then we'll go to normal shock table to find the Mn2, P2 by P1, T2 by T1. I think here P0 is not necessary. If you want, you can write it. So once you know the Mn2, you can find the M2 because we know both beta and theta. And we know P1, T1, you can find P2, T2. So they are given theta and Mach number. Beta is around 46. From that, they are finding Mn1. Then using normal shock table, they are finding all other ratios. You know P1, T1, you can find P2, T2. Using the formula, you can find M2.